Well, this seems like action packs. I've been a fan from them, basically.
Everybody here is here? Okay. Well, first of all, thanks for coming to this late afternoon session. I realize it's the end of a long day, so I'm going to try and keep this particular talk relatively lightweight and kind of a overview filled with name dropping rather than with real theorems. But in the subsequent lectures, I will try and delve more into the technical content. So normally I thank the organizers for inviting me to give a talk, but I'm one of the damned organizers, and I feel like now chastising myself and my fellow organizers for coming up with this bright idea of giving 5 talks in a row. But anyway, here we are. We've committed to do it, so let's yeah. Thanks, Fokion. Right. So, as Fokion mentioned earlier, part of the purpose of this program is to bring together the different strands, but not just the different strands within the program, but also to make connections with the other strand running in parallel on uncertainty in algorithms. So, perhaps the probabilistic strand within our program is the one that connects most, but as you will see, it's actually very different from the kind of work that goes on in probabilistic algorithmics. So here's a quick overview of the talk that I'll give today. I'll say a bit about programming languages for probabilistic programming. I was very fortunate to have the whole boot camp kicked off by Professor Scott and his call to arms to develop a formalism for reasoning about probabilistic programs and giving a semantics to it. So I'll talk about these early programming languages, say something about probabilistic transition systems, and then a bit more about recent developments, and finally I will say what's in the course. Okay, so why probability? So James Clerk Maxwell is famously said to have called probability the true logic of the world. And this was, of course, in 1850, and of course he made fundamental contributions to the use of probability in statistical physics, apart from inventing electrodynamics. So Clerk Maxwell's quote here I find very compelling, because it's really telling you that if you're dealing with the real world, you have to deal with uncertainty, and the only well-grounded formalism we have to tackle uncertainty is the calculus of probabilities. So this is Berkeley, and when I was growing up, I was listening to a song called "The Age of Aquarius." So it turns out, recently, well, not so recently, maybe 10 years ago, David Mumford, a well-known Fields medalist in algebraic geometry, became a convert to the theory of probability, and he wrote a paper called "The Dawning of the Age of Stochasticity," in which he argued that, in fact, old-fashioned Boolean logic is not the proper foundation for mathematics. It should be based on probability. Okay, so I won't read out the quotes, but if you just Google "Dawning of the Age of Stochasticity," you will get a link to Mumford's paper. In fact, Mumford is reputed to have told people when he was deep in his algebraic geometry phase that probability theory is all rubbish and it's not interesting, and he publicly admits that this was a big mistake, and he recanted that and really now espouses probability as a fundamental way of thinking about both mathematics and the natural world. So one of the things that I find when I got into probability was the thing that jumped out at me was the notion of conditional probability, and to me this is the probabilistic analog of the basic notion of logical inference, which is the engine by which we make deductions. So in ordinary logic, we have this notion of P, and P implies Q, leading to this new deduction Q, which can be written either as a rule or as a formula. And now in the probabilistic world, you introduce the notion of conditional probability, which can also be written in an analogous form, and it's suggestive. It says that the probability of both A and B it can be obtained by the conditional probability of A given that B has happened together with the probability of B. So here again, what this conditional probability is doing is it's saying, now you've learned something. You've learned that B happened. How do you revise your estimates of the probability for A? Okay, so this whole notion of conditioning is very evocative of how logical inference happens. And it becomes an important feature of probabilistic programming languages as they are now emerging. So conditioning, sorry?
Should we read anything into the fact that from the second to the third you change the intersection to a conjunction?
No. Please don't read anything into things like that. So as I said before, conditioning allows you to revise your probability estimates as you gain information. And there is this thing that's grandiosely called Bayes' theorem, but it's basically just a rewriting of that formula. But what it tells you is how to revise your estimates of the probabilities of certain hypotheses holding as you make observations. Okay, so this formula basically says you start out with some assumption about a certain hypothesis being true, a certain probability estimate for how it is true. You make some observations, and then you revise that probability estimate given that you've actually made a specific observation. Now, of course, you can ask in this Bayes formula, what happens if the probability of B is 0? Now, of course, in the discrete world, you can say, well, probability of B greater than 0, strictly greater than 0 is a side condition to that, because if probability of B is 0, then it can't have happened. So you can't be talking about the probability of A given B. Now, but this is a very naive point of view. In the continuous world, it very much often happens that one of the variables that you're looking at is a continuous variable. The probability of any one specific value is 0, yet you have to, you make an observation, you get a value, and you have to revise your probability estimates. So you need some new machinery to deal with that, which comes about when you start looking at probability theory on continuous spaces, and that will be a significant part of the mathematical stuff that I have to expound tomorrow. Okay, so in continuous spaces, you cannot just dismiss this case. So you need conditional probability distributions, or as they're called, regular conditional probability distributions. And somewhat charmingly, they're also called disintegrations, in contrast with integration. Nothing is collapsing. So, so that's a kind of overview. So let me just very quickly recapitulate very basic definitions so that we're all on the same page. So basic discrete probability, you have a finite set called the sample space. Subsets are called events. And you have a function that assigns probabilities to elements of S and hence to events, because then probabilities of an event are just obtained by summing up the probability of the individual members of each one of those components of the set event. A random variable is just a function. It doesn't have to be real valued, but let's just take it to be real valued, which maps S to R. And what happens is that when you have such a random variable on a space on which a probability distribution is defined, it induces a probability measure on the reals. Okay, so you get a probability distribution induced on X simply by this standard formula. Basically, you look at the inverse image of a set in R and ask which are the points that could have landed you in there, and you measure them according to the probability distribution on your sample space. Somewhat charmingly, probabilists use this kind of notation for talking about random variables and their probabilities. It tends to violently conflict with the way measure theorists and analysts use their notations for talking about measure and probability. But then, as somebody said, probability theory is measure theory with soul. So this is perhaps the more soulful way of writing probability expressions. A very fundamental concept is independence. We say two events are independent if their probabilities of both of them happening are just a product, so they don't interfere with each other in any way. And again, two random variables are independent, roughly speaking, if the induced probability distributions are independent. So now, as I said, conditioning is important. So one can talk about conditional random the independence of random variables conditioned on a third. So if we have three random variables, x, y, and z, we say x and y are independent conditional on z if this particular formula holds. So if you look at the conditional probabilities, they factorize. Okay, and it might well be that the probabilities themselves do not. They perhaps are correlated because they both depend on Z, but once you fix Z, they become independent. So this notion of conditional independence is actually a very important thing and has become crucial in machine learning. If you have 3 or more variables, you can define pairwise independence and mutual independence. And just as a curiosity, these are not necessarily the same. So here's a simple example. Supposing I take 2 tosses of a fair coin. So this defines my sample space, and I look at the following 3 events. The first event says the first toss is an H, and I don't care what the second toss is. B says the second toss is a heads, and I don't care what the first toss is. And C says the 2 tosses give the same result. Now, all 3 of these events have probability a half. If you look at the probability of any pair of them, it's a quarter, so they're pairwise independent. However, the probability of all 3 of them is also a quarter and not an eighth. So they're not completely independent, it's just pairwise independence. Okay, so this was a simple but curious example that often people seem not to realize. So probabilistic models become important. Reasoning under uncertainty involves the interplay between independence and conditioning. And a very powerful formalism invented by people in AI called Bayes nets allow you to work with probabilistic models representing precisely these 2 key features, independence and particularly conditional independence, and how to compute marginal probabilities in a simple and efficient way. So the hugely successful framework is called graphical models. I'm not sure if it was invented by Pearl, but certainly highly popularized by Pearl, and Kusha is nodding vigorously, so I assume invented by Pearl.
That's what he won a Turing Award for, well.
So I know he pushed the theory a lot. I'm not sure if he wrote down the first one, but it doesn't matter.
Bayesian networks were more or less invented by Pearl, but Markov networks and so on had been considered earlier.
Okay. So we have this framework for representing Bayes nets, and what happens is that this conditional independent structure captures the crucial features of the model in a compact way and is so useful for computing both marginal distributions and conditional probabilities efficiently. So these models are indeed useful for many situations, but one important thing is that they're not compositional, and they often flatten out the structure inherent in a situation. Okay, and so one of the criticisms that emerged, in fact, from the machine learning community is that these models are great when you have them, and you kind of build them from scratch. But if I have a couple of these models and I want to combine them, how do I compose them? So perhaps you might have a subgraph that's repeated many times in a regular pattern, and you'd like to say something like, oh, I need some kind of iteration construct to repeat this. So a new hope emerges from the theory of programming languages, because if I can say one thing that programming language semantics is about, it's about looking for structure and composition. In fact, the second workshop in this thematic semester is called compositionality. No, sorry, the third one. The second one is called symmetry. The first one, I should say, is called uncertainty, and many of the things that I'm mentioning today, the speakers at that uncertainty workshop will be elaborating on some of the points that I make today. So here's this new hope. Use the theory of programming languages to give a structural way of presenting and reasoning compositionally about probabilistic models. So this is what I'm hoping will emerge from this whole theory of probabilistic programming languages. Other things have happened since, let's say, 1985. One of the pioneers in reasoning about probabilistic systems was Moshe Vardi, who in 1985 considered model checking of probabilistic systems. And subsequently, there have been hugely successful developments. So I guess Marta Kwiatkowska, who will also be at the uncertainty workshop, developed a highly successful system called PRISM, with which she has performed many industrial strength case studies for reasoning about probabilistic systems. And others named there have also developed a theory of probabilistic verification. Jane Hilston wrote a landmark thesis over 20 years ago using a compositional probabilistic process algebra for analyzing performance of computer systems, again in a compositional way. So again, the theme of compositionality is very fundamental. Probabilistic transition systems were studied by several people, Kim Larsen, Ernest Koh, von Glabeck, and various others. And concepts like bisimulation and so on, which I will be talking about in lecture 4 at some length, came out of this work. Around 20 years ago, a number of people started looking at probability theory in this sense of probabilistic transition systems on continuous state spaces. So so I guess one of the early papers on this was a paper we wrote in LIX 1997 and another one in 98, where we started looking at what bisimulation was and proved a logical characterization of bisimulation for these continuous state spaces. And others got involved, notably Mike Mislov sitting in the back there, and his postdocs and co-workers. One of the things that came out from studying probability and other kinds of quantitative theories is that the algebra of programs is typically stated in some kind of equational system. You say this and this program is equivalent to that one. We saw Fokion's lectures in relational algebra, where essentially you are making equational statements about transforming one expression to the other. When you have this quantitative kind of setting and you start talking about equations, it becomes a bit suspect, because you perturb the description of the model just slightly, and then suddenly you say, aha, these things are not equivalent anymore because the numbers don't match exactly. And you wouldn't like to just say, oh no, they're not equivalent anymore. You'd rather say they're close by, even if they're not exactly equivalent. And so one is led to the notion of using metrics and approximations to reason about probabilistic and other quantitative systems. One of the vexing problems, and I say vexing advisedly, is combining probability and unquantified non-determinism. And this has led to a lot of complicated and difficult to read papers by various people. I mean, they're difficult to read because the subject is intrinsically hard, not because it's not presented well, but there have been a lot of interesting developments. Mike Mislov, again, was one of the pioneers in this work. So let me say a bit now about probability theory and domains. Mike will be giving a talk tomorrow at the end of the day on this subject, so I won't say much, just historical remarks at this point. Saheb Jahromi in 1978 developed probabilistic LCF. So LCF is the logic of computable functions, which was originally developed by Dana Scott and then pushed by Robin Milner and analyzed at great length by Gordon Plotkin in the context of LCF as a programming language. Saheb Jahromi, around that time, in fact, developed a probabilistic variant of LCF, and in order to understand the semantics of this language, which he had to develop probability distributions on top of domain structure. So domain structure is a kind of mathematical partially ordered sets that one finds essential to give semantics to the lambda calculus. And now what we see here was this new feature, higher order language, but with probabilities only at ground type. But already the combination of higher type abstraction and probability is occurring. About a decade after that, Claire Jones and Gordon Plotkin developed the probabilistic power domain, which they intended to use to give a full-blown higher type probabilistic programming language. This power domain was a fantastic technical achievement, but this also was problematic. Regina Tix and Achim Jung showed that this was, again, a vexing construction. So basically, there is no known Cartesian closed category suitable for programming language semantics in which this probabilistic power domain is closed. So it's there, but it's and it's kind of like a shining beacon of achievement, but it's also doesn't fit well with how we like to think about programming languages at higher types. And Abbas Edolat also extended integration theory onto domains. Back in '81, Dexter Kozen gave us simple semantics for a language with while loops. So in this language, you had just an ordinary assignment statement. You had sequential composition, a conditional, and the while loop. And so the question was, how does one give semantics to this? So you notice there's nothing probabilistic in the language itself, but the intention was the variables are not described by actual values, but perhaps governed by probability distributions, and you want to know how are those distributions transformed by the execution of the program. Okay? If you wish, you can add some kind of random choice construct to the language. It's not at all difficult. I chose not to do it here.
So are the functions uninterpreted, or what is what is?
So you imagine that there's some stock of standard functions that you're using. Yeah, like some arithmetic and so on, which I didn't want to, yeah. But I mean, you can make this language as rich as you like by enriching that f, but yes, some let's say some generic f's that allow you to do basic arithmetic. Already you have to deal with all kinds of interesting things. So the first thing to note is you might say, look, I learned probability theory by tossing dice and tossing coins, rolling dice and tossing coins, and it was completely adequate. Why do I need all this fancy measure theory that you're talking about? As soon as you introduce something like a while loop or recursion, you are going to get into the realm of probability theory on continuous state spaces. So you have no choice. It's going to happen anyway. So the semantics, which I will describe in lecture 3 in some detail, I'll just say roughly what it does here, is that the programs transform input distributions to output distributions. So they are distribution transformers. And in this sense, you can think of them as what we often call state transformer semantics in operational semantics. You have some description of the state of a program by telling you, for example, what the values of variables are. You execute some code. The variables get updated in some way, and this semantic description of the language simply tells you this is how a state transforms to a new state for this particular construct. So Kozen semantics was exactly in that spirit. But he also gave a so-called backward semantics, where you look at expectation values of functions on the state as they transform backwards. So if I tell you the expectation value of a certain function after a program fragment is executed, I can then infer what the expectation value was before. Okay, and so this gives you a kind of backward flow semantics. And if you're familiar with programming languages, there's this thing called weakest precondition semantics that Dijkstra invented for reasoning about programs, imperative programs. And so this is the probabilistic analog of that. So both these things were in Dexter Kozen's original paper. And there were many contributions thereafter from the Oxford group, headed by Tony Hoare and several of his co-workers. And Carol Morgan and Annabelle McIver are still very active in this area of reasoning about probabilistic programs. So around 1997, Saraswat, Gupta, and Jagadisan combined probability with the concurrent constraint programming paradigm, which you may or may not have heard of. So I will give you a small summary of it presently. And later on, we threw out Vijay and added me and added recursion. So we showed that there were some interesting computational effects that had no pure measure theory counterpart. So I'm going to spend a lot of time talking about measure theory in this sequence of lectures, but I have to say right up front, I think measure theory is the wrong thing. It has some fundamental flaws. One of them is things are always defined up to sets of measures 0, and you're always wondering about things being almost everywhere true, etc. And it seems to me that one should be working with other ways of doing it. Okay, so what was interesting about this concurrent constraint paradigm is conditioning became very explicit in the framework, as I will show you in a minute. The paper at that time was largely ignored, but now is a good time to revive it in that case. So here is a kind of cartoon picture of how the concurrent constraint paradigm works. There is, you might think of this cloud as being a store, which is just a first order formula. So these are facts that you add to, let's call it a collection of a store of facts. Okay, so various processes interact with this store. So these ovals represent processes that are interacting with the store, and they do not interact directly with each other. The concurrency is mediated through their interaction with the store. And what do they do with the store? They ask whether the store entails a particular formula. So you can say, I ask, is x positive, or is x equal to y? And if so, then do something. Otherwise, suspend and wait. So you see that ask construct is kind of a synchronizer. It tells you, wait until this is true. Okay, it's not a conditional in the traditional sense of, if this is true, do this, if not, do something else. No, if this is true, you get to go ahead, otherwise you're suspended and stopped. They can also tell formulas, so they can add a new formula to the store. So the store is actually growing. It's not like in a functional language immune to side effects. It is being side affected, but in a benign way. The information content of the store is always increasing. In a normal imperative program, when you do things like x gets 1, you're not just updating the value of x, you're also killing the old value of x. Okay, so you're destroying information as well. That's never happening in this particular setting. And how do we know whether the formula in the store entails the formula you're asking about? We abstract away from that. We pretend there's this daemon who answers the entailment queries. Of course, there's a fascinating subject about the algorithmics of answering constraint queries, but we're abstracting away from that and just saying somehow this daemon answers entailment queries. So that's the ask-tell model. So this is the syntax for the CCP processes. You can ask a formula, you can tell a formula, you can run two processes in parallel, and then you can have a fresh local variable, which we call new x. So the scope of this new variable x is p, and so you can introduce fresh variables into the store. You can then impose constraints on it, and so on. And we add recursion as well. So it turns out, that there's a very nice semantics for this programming language in terms of what are called closure operators. So the set of stores forms a complete algebraic lattice, and programs, what they do is they can only improve the information content of these stores, and so they are modeled as continuous closure operators on top of that lattice. Now, for the probabilistic variant, you add this new construct, choose x from some finite domain, and so this variable x again is a local variable whose scope is p, but now it's assigned a value that's randomly selected, perhaps uniformly, from some domain d. Okay, so these things should not have been called random variables, but at that time we were so naive, that's what we called them. So each of these variables has its own independent probability distribution, and you might think it's very limiting that you're always only using the uniform distribution, but in fact, by judicious use of constraints, you can show that you can get any distribution you want as long as the probabilities in question are rational. Okay, so conditioning and constraints interact like this. So you can do things like choose x from this set. So the probability of getting one of those values is a quarter, but then you can impose this constraint, x has to be less than 2, less than or equal to 2, and then you can have these two things running in parallel. Ask this, in which case you add a to the store, or ask that, in which case you add b to the store. They're both sitting there. So depending on what value gets assigned to x, then one or other of those things will trigger. You might note that it's possible that x gets the value 3, which will of course flatly contradict this constraint, in which case the store is said to become inconsistent, and we kind of discard those stores and normalize, renormalize the probabilities. Okay, good. So that's an example of a concurrent constraint programming language with probabilities. What's nice about it, of course, is the explicit use of conditioning and the explicit ability to write those kinds of things down in your models. So many people were interested in verifying probabilistic systems. So such systems feature probabilistic components, protocols using randomization, Bluetooth, controllers, etc., cell phones. And so people were, especially people actually building these verifiers, were looking for ways to model probabilistic transition systems as abstractions of real systems. And of course, they were also developing logics for reasoning about probability. So let me describe briefly the label transition system.
Prakash, you mentioned already several different probabilistic programming languages. What is the way, how do we compare them? You know, before we have expressive power, but what is the analog here for?
Well, expressive power is always the standard by which you try to compare them. But mostly, I mean, how do you compare existing programming languages, right? You try to ask which ones are the best for being able to smoothly express certain kinds of computations you want to do. So what happens in this world is, I mean, it's a good question because this is a subject really in ferment right now. And people are exactly having this argument. And the argument has to emerge from, well, what is it you really want to do? And what is especially emerging from the people in machine learning who want to use probabilistic programming languages is they want to write these models that capture conditioning. So it becomes crucial for them that that's kind of a basic feature of the language. So in terms of formal comparison, in the sense of a theorem, like everything definable in this is also definable in that, such theorems tend not to be interesting because you can pretty much always do that by, you know, some kind of fiendish coding if necessary. So it becomes a more subjective thing about which language you prefer to use or how you design the language. So let me define labeled transition systems. So these were models of things that we are attempting to use as abstractions of systems that we believe have some probabilistic feature, and we want to reason about them, talk about their properties, and about equivalence. So you have a set of states, a set of so-called labels or actions, hence label transition system, and a transition relation, which is a triple like that, which takes a state, an action, and another state. It's typically not written as a triple. It's one likes to use the label and to annotate an arrow and describe this as a transition relation. So these transitions in general could be indeterminate. Okay, so the same transition from a given state could lead you to one of several different states, and not in any quantified way. So these are called non-deterministic transition systems. All right, so we will write it with the label on top of the arrow. Now, probabilistic transition, so this was, of course, studied at great length, particularly by people like Milner and others. And they developed, Milner and Park, I guess, and others. And they developed important fundamental notions like bisimulation, when are two states equivalent in their behavior, and and other notions like weak bisimulation, etc. In fact, one ended up with a zoo of possible equivalences. For discrete probabilistic transition systems, it was just like an ordinary label transition system, but with probabilities now associated with the transitions. So again, you have a set of states, a set of labels, and for every label, you get, instead of a relation, you get a transition probability matrix. So with every pair of states, you associate a number, and that number you should think of as the probability of jumping from the start state to the end state. Okay, so you can think of this actually perhaps better as state to distributions over states. So this kind of model is what's called reactive. All the probabilistic data is internal. Which label is selected is something that's left up to the environment, or perhaps the image you want to use is of an experimenter coming there and pressing buttons on your box so that the system reacts to the experiment that is being performed on the system. Okay, so we're not attempting to associate probabilities with how those labels are selected, but given that a particular label is selected, this is how the system reacts to it. There are other models where you also say, okay, so these and these actions happen with these probabilities, so those are called generative models. I will look at reactive models. So here are some simple examples of probabilistic transition systems. So for example, the state S0 can jump to S1 or S2 with the action A with the indicated probabilities. S2 can jump to S3 with probability 1 under the action A. And over here, you see that some states, S2 cannot do a transition with the action C at all, but S1 can, and it scatters you between S3 and S4 uniformly. As I said before, we're not trying to assign probabilities of doing an A or a B, so you have two probability 1 transitions coming out of S0. So A will definitely take you to S1, B will definitely take you to S2, and I'm not attempting to model with what probability does A or B happen. That just happens. And you are trying to express how does my system respond to external stimuli. Okay, so one of the things that we will get into later on is the notion of equivalent behavior of different states of this system. So this is the concept called bisimulation, and the sort of the deepest result I will try to show you is a logical characterization of that bisimulation relation. So what happens now in the recent developments is this emergence of probability at higher type and also conditioning as a basic primitive. So as I said, back in '99, we had already concurrent constraint programming with probability, so that had probabilities and constraints and conditioning, but a couple of interesting new languages have emerged, Church and one called Tabular. So Church comes out of the group at MIT, so it includes Vikas Mansingha, Dan Roy, and others. And Tabular is from Microsoft, Cambridge, I think headed by Andy Gordon and several others. So the Church people will be here actually for the uncertainty workshop. And there will be many interesting things that they will talk about. Domain theory in conjunction with probability, I've already mentioned Sahib Jaromi. Back in 2002, Norman Ramsey and Avi Pfeffer developed a kind of monadic language for, again, an LCF type language that worked with probability. Ugo del Lago, who was also mentioned by Professor Scott this morning, has done many papers on operational semantics of lambda calculi with probability. Varaka and Gubo-Larhek have also developed domains of random variables. So there's a lot of things happening now with probability at higher type. And of course, Dana Scott himself described this morning showing that a model showing that random variables can be introduced into the lambda calculus. So these are all proposals, and I would say at this point there's quite a lot of ferment and argument about what should be the right models, how should one reason about these things, what kind of theories should one have. And very recently, so less than maybe just over a month ago at LIX, Sam Staten and his co-workers presented a semantics for reasoning and reasoning principles for a higher order probabilistic programming language. I found this to be a really remarkable piece of work. Sam will also be here at the uncertainty workshop talking about, presumably about this. Also at LIX, Radu Mardare and I and Gordon Plotkin introduced a new kind of equational logic. So it works roughly like this. So we have the equality relation that one is familiar with. We annotated it with a small real number epsilon, and it allowed us to state things like, some term is within epsilon of some other term. Okay. Now you might think this is just a naive hack. Surprisingly, you can actually develop a nice equational theory, a nice analog of usual equational theory using this idea. So normal equational theories correspond to finitary monads on set. It turns out that these things correspond to monads on the category of metric spaces. So there's a nice, in fact, the theory develops in a nice analog. Sorry?
Where are the probabilities?
So the key examples of using this is for reasoning about collections of probability distributions. So probability distributions, it turns out you want to compare them, and you typically make them into metric spaces. And there are very crucial metrics that one uses to compare probability distributions. One of the most important ones is called the Kantorovich-Wasserstein metric. So one of the things we found is that that particular metric can just be axiomatized in a very simple way with a few equations in this generalized sense of equations. So I will talk about the Kantorovich metric also in some of my later lectures. Okay, so this is some of the recent work about approximation. Now, I want to close with a bit of a shock, which I got in 2011. So this is a paper by Nate Ackerman, Cameron Freer, and Dan Roy. So what they showed was that there is a pair of computable random variables such that the conditional probability distribution is not computable. So you can have purely computably defined measures, you can have computable conditions on which you're conditioning, and then you condition it, and the damned conditional probability that you get is not computable. So this was a fiendishly clever encoding that they had to do this, but I think for all of us it was a shock. So again, this is creating some confusion about, you can't just allow freewheeling conditioning in your programming language. You need to control how we do it. And so this is amongst the things being debated and thought about at this point. Okay, so let me just end by saying what's happening in the next 4 lectures. So as I said, this lecture is somewhat short. The next one will perhaps be, I'll be hard pressed to press it into an hour, because I'm going to try and cover a 1 semester course on measure and integration. But perhaps I will randomly select topics from within that. In the third lecture, sorry?
Topics of measure zero.
Hopefully more than that. So in the third lecture, I'd like to present a particular monad that was originally proposed by Lauvier back in 64, maybe 62. It was never published. There are notes circulating with typed up and with people's handwritten notes in the margins. And if you're in the inner circle, you get your hands on a copy of this. But now these things are being publicized, and so you can get your hands on it. But in 1981, Michel Giry wrote a beautiful paper in which she developed not just the Lauvier monad, but a new one on Polish spaces. So, and worked out in some detail. And so this monad turns out to be fundamental in everything that's happening now in probabilistic programming languages, in reasoning about probability, probabilistic transition systems, because it captures the correct probabilistic analog of the notion of binary relation. Okay, so binary relations are very basic fundamental things. You might ask, so what's the probabilistic analog of a binary relation? It turns out to emerge from this particular monad. Okay, so
for that lecture, are you going to assume we're familiar with monads?
No, I'm not. I'm not even going to assume that you're familiar with the power set.
It's stuck in a semester's worth of
category theory in the second lecture, yes. Not a semester's worth, just the first month. In the third lecture, I'd like to talk about bisimulation of probabilistic transition systems on continuous state spaces and prove this theorem on the logical characterization of bisimulation. So such a theorem was first proved by Larson and Scoe back in 89, 91, depending on whether you look at the conference or the journal version. I think 91 is when the journal paper appeared. But it was for probabilistic transition systems on discrete spaces. And it had a very strong assumption, which was that all the probabilities appearing are multiples of some smallest real number. So there's some smallest number, 0.01 or whatever, and every probability must be some multiple of that, some integer multiple of that. So it was a strong finite branching assumption built into it. The logic had negation. So it sounds like I'm trashing it, but it was actually a breakthrough result at the time. So when we started doing probabilistic transition systems on continuous state spaces, we were not very optimistic because, finite branching assumption, this is not going to work if you're looking at things that are diffusing, for example, on the real line, absolutely not finitely branching in any sense of the word. How is this going to work? What even is the syntax going to be like? And surprisingly, it turned out that a logic simpler than the one that Larson and Skow used sufficed to characterize bisimulation even on these continuous spaces. It did not need any of those finite branching assumptions. So in fact, because the discrete thing is a special case of the continuous one, it was also an improvement of the discrete results. And it didn't use any of the standard clever combinatorial techniques that one uses in the discrete case. Instead, it used some remarkable properties of analytic spaces. And again, I'm not going to assume you know what those are, but those are a certain kind of topological spaces that arise in measure theory. So this is the one proof that I will go through in some detail. And finally, as I said, it becomes very important to metrics and measure theory have a funny relationship. A priori, you might think, what the hell does metrics have to do with it? You have measure theory, you have abstract notions of sigma algebras defined on arbitrary sets, and you crank away. Why should metrics play a role? Well, two things happen. So measure theory works particularly well on certain kinds of metric spaces called Polish spaces, which are the topological spaces underlying complete separable metric spaces. So measures play well with metrics, and you also want to make your space of measures into itself a metric space, because it turns out to be important to be able to understand how close measures are. And the theory of metrics between measures is a beautiful one. And I think really there are many metrics that one can define, but the most interesting and remarkable one is due to Kantorovich, which was developed in the context of mass transportation problems during the war. So Kantorovich and his student Wasserstein and his other student Rubinstein developed this theory. So this is now available in the literature. It's quite difficult to track down these names because, first of all, sometimes it's called Kantorovich metric, sometimes it's called Wasserstein metric. Wasserstein is spelled 5 different ways. It's presumably spelled one way in Russian, but it's transliterated into English in at least 5 or 6 different ways, V, W, apostrophes here, there, and everywhere. So it becomes a bit difficult to track this down. For a long time, we used to call it the Hutchinson metric because we learned these things from Hutchinson's work, reading books on fractals. But Frank van Bruegel, who's a very scholarly person, actually emailed Hutchinson and said, "Did you invent this?" And Hutchinson said, "No, good heavens, it's been around for years." So he actually tracked it down, and we've now started calling it the Kantorovich-Wasserstein metric. Sadly, the people in computer vision also independently discovered this metric, but they started calling it the Earth mover's distance. And so if you try to find out, if you try to Google this thing, you will find Earth mover's distance now, I think, drowning out Kantorovich metric in the number of hits you get. So, right, so that's what I will talk about in the very last lecture. I will introduce the Kantorovich metric, or at least a kind of discrete version of it, and tell you how to use this to define metrics between Markov processes that measure their behavioral similarity. So things at 0 distance will be bisimilar, and things not bisimilar will be some distance away. Okay, and it turns out, of course, that this will depend in some sense on this logical characterization, because it will capture some of the intuitions that come out of that logical characterization. All right, so I will end 10 minutes early today, but not tomorrow. Perhaps I will end 10 minutes late tomorrow, who knows. So are there any questions? Yes?
Bit vague, but you started off with the analogy between implication and conditional probability. Something that's always bugged me is that there's a disanalogy, that you can iterate implications but not conditional probabilities. Is that somehow related to the issues with compositionality, and does that have any connection with what I was trying to do with probabilistic programming language?
So I've never thought about it like that. So one doesn't try to iterate conditioning in the typical probabilistic programming languages that are emerging out of the machine learning community. So when one is talking about iteration there, it's more like you want to iterate some kind of propagation rather than some kind of conditioning. This particular, yes, there is a disanalogy. On the other hand, it's only an analogy, not a perfect correspondence. But the analogy goes further than maybe I'm selling it. So I mean, as you know, there is this nice category called SRL, which captures some aspects of conditioning and composing. So anyway, we'll see more of these things. Okay, on.
Go back to the slide of the result of Ackermann, Freer, and Roy.
Yes.
Two questions. What is does it really say that the joint probability is not computable, and what?
Well, the conditional probability.
But what can you use Bayes' rule? What makes it?
So this is on continuous spaces, so it's not the naive form of Bayes' rule. But
and I know these guys, Ackermann and Freer, have done work on graph limits. Is that is this totally different way?
it's totally different from graph limits. Yeah, but
Is it conditional expectation?
conditional probability. So Roy is a machine learning person and Freer is a recursion theorist. So they got together and brewed this hell's brew.
But I'm not sure I understand. If it's on continuous spaces, then what does computable random variable mean?
Yeah, so there is all that. One has to talk about computable real numbers and things like this.
Oh, so such a claim is not true in the discrete world.
No, definitely not. Yes, certainly not in their, according to their paper. No.
I mean, what I mean by discrete world is not finite, but countable. So if I have a random variable on a countable sample space, is there such a claim?
I don't know. One will have to check. Certainly their paper was not like that, but it wouldn't shock me completely if it was even true in the countable case.
And their computable random variable presumably means I give you some particular value that the random variable, so the probability that the random variable is going to evaluate to some particular value is computable. Is that?
Yes, that's right. Freer and Roy will both be here for the uncertainty workshop. So I think, in fact, Cameron is going to present that in his talk. Okay, so if there are no more questions, maybe we should break and have a drink.